Thank you, everybody, for your flexibility. I'm sorry I wasn't able to make it there in person. But I'm going to go ahead and just start off by diving into what TensorFlow Lite for microcontrollers is. It's a pretty long name, so let's break that down and understand, to start with, what is TensorFlow Lite? So a lot of you will be aware of TensorFlow. TensorFlow Lite is part of the TensorFlow family. It's aimed at running machine learning on mobile and IoT devices, things like the Raspberry Pi. The usual criteria we look at here is anything that's capable of running something that's like Linux. You can probably get TensorFlow Lite up and running on it. It has a converter for going from TensorFlow models in the training environment into something that you can run for inference. And this is quite an important point, so I'll be coming back to that in some of my later slides. And the magic here is that it takes something that a researcher has put together in a cloud server GPU training environment and turns it into something that is executable as an inference model for doing predictions on device. And this also has to do a bunch of post-training optimizations. Things like, oh, you've got batch normalizations in your training model. It has to figure out how to get rid of them, has to figure out how to get rid of everything that's involved in the back propagation pass, and anything that's around sort of debugging or is particularly specific to the cloud environment. It uses an interpreter to run the models that have been produced, and this is something else that I'll be coming back to because there are some design choices that have been made around this that I think are pretty interesting to dig into. It's graph-based, so we have a list of dependencies between ops, and the interpreter runs by taking a topologically sorted set of ops and running through them one at a time. And each node in the graph is a computation operation. You can think of these as layers if you're thinking about the perspective of creating a model in a training environment. But another really interesting point is how you actually break down a set of computations into individual sort of chunks. There are choices where you can either break them up fairly fine-grained into things like pure mathematical operations like add and matrix multiply, or you can bundle them together into things that are more like what users are thinking about, like, oh, this is a convolution layer, which might include an add and matrix multiply and maybe an IM2 call or something like that. So we've actually taken a fairly opinionated idea of what we think are fairly efficient ways of bundling the ops together into sort of particular fused operations that we use within TF Lite. And one thing that's important for TensorFlow Lite, but really doesn't come into play nearly as much for the microcontroller side, is for TensorFlow Lite, especially on Android, you never know what hardware you're actually going to be deploying on. You don't know if the phone that's going to be running your app has a GPU that's worth using. Maybe it has a specialized NPU. There are all sorts of other hardware resources that might be useful to use, but that you don't know when you're actually putting your app together. So the TensorFlow Lite interpreter actually has runtime delegates that figure out, hey, I've got this hardware accelerator, I'm going to offload some of the work from this model into that. So there's actually some quite sophisticated work that's being done there to figure out how to use these accelerator pieces of hardware. And it seems to have worked pretty well. We've managed to get out onto billions of mobile devices in production. It's a long way from being perfect. It's definitely not the last word in how we're going to be doing this. There's a lot of great work being done across the board in the mobile space. There's some awesome stuff that's happening. I would call out sort of CoreML have been doing great stuff. PyTorch Mobile is really interesting and has some great features. But we've been pretty happy with what we've managed to do over the last couple of years in terms of getting TensorFlow Lite out into the mobile world and helping Google applications and a whole bunch of external apps as well actually do interesting stuff with machine learning. Now, I mentioned the converter. This is the #1 place where we have users running into problems, because it's actually surprisingly hard to go from a training environment to something that can be efficiently executed on a mobile device. And we're able to take, the first thing you have to do is actually turn the training graph, which there's an almost limitless number of ways that you can express things in Python in TensorFlow, into something that can actually be saved. So you need a saved model, you need a TF.Keras has nice integration, so pretty much anything you can put together in Keras, you should be able to have a good chance of converting down. And there's a whole new concrete function thing in TF 2.0, which I have to admit I don't understand well enough to actually dive into giving an explanation of, but which gives you another route. And you can do all of this through Python in your Colab scripts or in your Python scripts, or just directly through the command line. And one of the things that I've actually been very happy about as we've been working on microcontrollers is that we've been using flat buffers for the TensorFlow Lite model format. And this is a cross-platform serialization library. You might be wondering, oh, how is this different from something like protobufs? So what's really nice about them is that they store their data in a way that doesn't require any parsing or unpacking or copying. You can effectively just mem-map your data into memory and then just start accessing the information in the model right away without any further steps. So it's really nice in terms of just being able to use your memory most efficiently and being able to avoid any kind of like startup cost. And you can do things like, keep only the parts of the buffer that you're using in memory. Has an extremely small footprint, just very low single-digit kilobytes of code required to support this, whereas protobuf can easily in the hundreds of kilobytes to support something like TensorFlow's GraphDef. So this is actually was a nice surprise when we were diving into microcontrollers, which have very, very constrained memory resources. And it has strong typing, so there's lots of checking, and it has all of the things you'd expect from like a modern serialization library. And another very, very pleasant reason for using TensorFlow Lite as the basis for our microcontroller effort is that I think I don't know if Raziel is actually able to make it, but he has been leading the TensorFlow model optimization toolkit within Google. And it really is a fantastic set of resources for doing all sorts of things, from quantization to sparsification to pruning. That's all integrated with the model export process. And one of the key things that we've done over the last year is really tried to standardize on post-training quantization. We've tried a lot of different approaches over the last few years, and one of the biggest barriers to people adopting quantization we found has been that it's actually really hard to generate a quantized model. So post-training quantization is nice because you just go ahead and you train your model as usual, ignoring the fact that you're going to be deploying with quantization, and then the only obstacle is that you have to supply some representative data sets at the conversion stage so that you can figure out, so that we can figure out how to set the activation ranges correctly for quantization. The very simplest way to do this doesn't even require that sort of representative data set. If you just quantize the weights down to 8-bit, but then do all of the calculations in the graph in float, then you get a size reduction of 75%. If you really want to be getting the full advantages of quantization, though, you want to do that conversion to full integer, which does require supplying some representative data sets. And yeah, we focused on int8 input and output. We do actually have a page up on the website which talks about the full quantization specification. And if anybody gets lost on that, feel free to drop me an email at petewarden@google.com. And I'll also be sharing these slides with my email address on them. So I mentioned the easiest way of doing quantization is you just say, hey, I want all my weights quantized, and you really don't have to do very much more. You get a file that is instantly pretty much 75% smaller than it was with float 32 weights. And then full integer quantization, you actually have to pass in a bunch of inputs from a representative data set so it can figure out for every intermediate layer in the graph what the min and max values are likely to be, so that we can quantize to an appropriate range for each one of those. And we have API support for this in Python. We also have some experimental support around float 16 quantization, but I'm not going to dive really too far into that today. The TensorFlow Lite interpreter has a whole bunch of roles, handles all of the loading, handles operator registration, which is actually the way that we link up the operators that are listed in a model file with routines and functions that actually implement the computation that you need to do. And this is pretty important because you can have hundreds of different operators potentially, but they all take up a bunch of space in the executable. So you really want to make sure that you're only calling the operators that you actually need for your particular model. There's also hardware delegate selection. I talked about that a little bit. When your app starts up on, for example, Android, you don't know at publishing time what hardware the user is going to have on their phone. So the hardware delegate actually looks around, figures out what hardware is actually present, and tries to execute as much of the graph as it can on any faster hardware that's available. And at the core of the interpreter is the process by you set up the input to your inference model, and then you run invoke to actually execute the graph, and then you grab the output. So that was a whirlwind tour through what TensorFlow Lite is. What do we do about embedded platforms? So, here I'm talking about devices that fundamentally can't run Linux. Is, again, a good rule of thumb for the embedded side. So that's not Raspberry Pi. The Raspberry Pi has many hundreds of megabytes of memory, often gigabytes, and burns maybe 4 or 5 watts of power when it's running. So this is really looking at devices that have possibly only hundreds of kilobytes of memory, or even just tens of kilobytes of memory. And these devices fundamentally exist because they're very, very cheap. They can be 50 cents or less, and they're able to run often in very small amounts of power. So they can run on just 1 milliwatt or below. So that combination means that you can have these devices that are everywhere. There are already hundreds of billions of these devices out there in the world. And they can be in everything from toys to medical devices to agriculture. But the fundamental challenge is you have to fit within just tens of kilobytes of memory often. Now, there's been some really great work done before on this. One of my favorite early versions was by Neil Tan, Microtensor, which is still a great place to look for experiments and prototyping and research. SimSys NN actually has a really excellent bunch of work, especially around optimizing operators for these embedded devices. And there are proprietary sort of vendor-specific solutions like ST's Cube AI, which let you convert models into optimized code for their devices. Probably the most common solution, though, is that people will train a small model in a training environment, something like TensorFlow or PyTorch, and then they will figure out how to manually transfer that model as code functions into something they can run on their embedded device. So the common patterns that we've seen across all of these are the converter is really hard. I've written my own kind of inference frameworks, and it's always having to deal with the conversion process from training to the inference representation that you want. That takes the most time. Even if you think you've got a good spread of models that are supported, I guarantee that the next customer that comes to you will have some model that's using some op that you hadn't thought of, or some op that you hadn't supported, or some combination of ops that doesn't work well for your converter. So it's very hard to scale writing a converter from a training environment to one of these specialized frameworks. And a lot of these solutions also work by generating code that you then import into a project rather than the interpreted approach that TensorFlow Lite actually takes. So this is where TensorFlow Lite Micro comes in. It started as a research moonshot within Google with just a couple of us in 2018, and it graduated last year into a fully fledged, real, fully supported project. And at its heart is a specialized version of the TensorFlow Lite interpreter that I talked about before. And the key attributes are that it's only got a 20 kilobyte runtime, but that it can execute existing flat buffer models. It will offer support across a wide range of existing platforms, and it's a fully fledged part of the TensorFlow team. So you can expect vigorous long-term support from us as we grow and expand it. And if you're interested, we have a chat room here that you can join for contributors. And we also have the charter of the whole SIG micro group, which is the special interest group for microcontrollers within TensorFlow that you're welcome to join. And I will be sharing these slides afterwards, so don't worry too much if you miss capturing these URLs. And the design principles behind this were we wanted no operating system dependencies. This means no file system dependencies, no standard C or C++ dependencies at link time, so that means no printf even, because printf alone can easily take up just 20 kilobytes, which kind of blew me away when I discovered that. And we don't expect there to be floating point hardware available, because there often isn't on the platforms we're targeting. No dynamic memory allocation. We do require a subset of C++11, nothing too scary, nothing crazy with templates or exceptions, but the flat buffer library we rely on does need C++11, so we've had to work with a few vendors to make sure their tool chains have been upgraded since it's only 9 years old, which is still a challenge for a lot of people. And we expect that they're going to be running on at least a 32-bit processor, which for a lot of people coming from the server world sounds a bit crazy, but we're still in this transition on the microcontroller side away from 8-bit and 16-bit processors. And we're only in the last few years are the majority of new devices shipping with 32 bits. So what is it that we're giving you with TF Lite Micro? So as I said before, conversion makes things incredibly hard if you're trying to do a standalone inference framework that isn't connected to a training framework. So if developers can't get a model into the format that you're expecting, you really won't get any pickup. And it means that it's also very, very hard to scale as researchers keep coming up with new models and new ops. You're constantly having to play catch up in order to support them. And the nice thing is that TensorFlow Lite already has to do all of this work for us. TensorFlow Lite, even just for our internal Google customers, we're dealing with a massive number of new models, every week. So we have to keep scaling all of this work. And so you can take advantage of everything that's being put into the conversion side by sort of using the same conversion that we are. And the model optimization side, even just beyond like-for-like conversion, is very hard. Like things like quantization, sparsity, pruning. I'm really happy to have Raziel's group doing a lot of that heavy lifting for us. By using TF Lite Micro, you sort of get this for free. And yeah, it's really nice, I found anyway, on one of my goals of the project, to actually have good definitions of what the underlying ops are. And by this I mean actual reference implementations that you can read and understand, that don't have dependencies on other math libraries like NumPy or Eigen or anything like that, that you can actually take into lots of different environments, and that you can reuse really in your own projects, and that come with unit tests that don't rely on you running the wider framework. And I think one of the other things that I'm hoping will be most valuable about this is having open source benchmark models that reflect applications and products that we need support and that we care about, things like voice recognition, things like activity detection, gesture recognition using accelerometers, even some image use cases, and that are trainable on open source data. So you don't just have to take these models that we've given you, you can actually try and come up with your own models based on the same data. And one example of this is the speech commands data set, which we've made available to help try and simulate what people need for wake word applications. And one thing, especially in this kind of research context, that I want to emphasize is that we're not trying to stifle innovation here. The embedded world I find really interesting because it has so many crazy constraints. You know, going down to like single-digit kilobytes sometimes you need to fit your program into. There's always going to be room for a lot of different approaches. I'm just hoping that some of the work we're doing here around things like the reference implementations, things like the conversion process, you can actually grab those and use them yourselves in your own projects. You know, for example, don't write your own export pipeline unless you really, really want to. Use our own export pipeline or grab our reference ops as a starting point and ignore our interpreter. We've really tried to design this framework to be very, very hackable and to be a box of Lego bricks you can reach into and grab what you need. And I'm really hoping that this unlocks a lot of research innovation because people will be able to start on things that are really novel and value added without having to wade through a whole ton of boilerplate before they can actually get something up and running. And the other nice thing is that hopefully if you're staying within, you know, some of these standards for things like exporting projects, users will actually have a really easy way to get started using your code because they'll already have a straightforward way to export the models. And I'm running fairly low on time, so I'm going to skip over pretty fast these interesting questions. But one thing I get asked a lot is why we're using the interpreter. And most other approaches use code generation, so that's a very good question. The biggest reason is that it's just the simplest way to do it. It's a lot easier for us to write code than it is to write code. Not having to kind of have this layer of indirection with the compiler in between us helps us keep our velocity and prototyping up. And there's no reason we can't still use code generation for op implementations, even if we're using an interpreter to call the ops. And it also allows us to deploy models separately from code. So we can actually do updates over the air, for example, without having to touch any of the code and just changing the models. And we do have a process called project generation to try and emulate some of the benefits of deployment using code generation by just being able to copy code. And I'm going to skip fairly lightly over these. But really what we try and do is make it so that you have a nice zip file full of source files that you can just drag into your IDE, and then things should automatically build there if you just build all of those files, so that you don't have to worry about using Linux and Bash and Python and everything like a lot of us in the research or academic or Google world expect to. And you know, another final thing that comes up a lot is like, why do we need a converter at all? We actually started off the first version of TensorFlow aimed at mobile devices, used the same code base as TensorFlow, but it was very large, and we still ended up having to freeze graphs and do other optimizations to go from the training environment to an inference environment, even though they were fundamentally the same representations. There was still kind of this impedance mismatch between the training environment and the inference environment. And I think one of the big questions is, are we going to come up with some kind of universal portable representation? I blame the researchers. They're the ones who keep coming up with like clever new ways to do things and improving on ops. As long as researchers keep coming up with new ops, it's going to be very hard to represent everything in some kind of frozen, locked down way. And a lot of the new ops that researchers come up with, you really can't represent except as C++ code. So this is a very tough problem. So if you want to learn more, feel free to drop me a line at petewarden@google.com. The code is and documentation is all up there, and I have an O'Reilly book out there as well, trying to run you through some of these examples. And I was trying to leave a few minutes here because I'd also been asked to give some closing remarks. And really what struck me in the preparation to this was that we're a really big community, and I'm disappointed I wasn't able to be present for many of the talks, but I looked through a lot of the submissions and there was some fantastic work coming in there. We're still trying to figure out where our home is in the research world. MLSys is actually a really great conference because it's something new. It's kind of the intersection of systems research and machine learning, which we didn't have before. So it's a lot better than some of the other places we were looking at. But on-device machine learning is kind of a very cross-disciplinary world. And we're still kind of trying to find the right venues, the right places to meet. And I think that's going to be an ongoing process. And it's one of the reasons I find it so interesting is because it does touch on so many different areas. Like there is all of this ML and systems and all of these hardware and all sorts of other research areas, alongside just a big dose of straightforward engineering to make some of these research ideas into something that's actually testable. And with that in mind, I really wanted to kind of highlight some of the areas where I'd love to see more research. One thing that's fascinated me has been that in the image world and a lot of the high-end research world, even things like the DeepMind's WavNet and a whole bunch of the other cutting-edge models don't use any feature generation at all. They take in the raw images, the raw audio, and they actually they feed that through their networks directly without any intermediate step, and then output the results at the end. But at the low end, we still seem to be doing a lot of stuff, like in the audio world with FFTs, with accelerometers. I've been doing things like subtracting gravity and trying to, do other sort of pre-processing and feature generation. Is this something that's just fundamental to our resource constraints, that we end up having to do these manual hand-tuned feature generation? Or can we come up with better approaches that are resource efficient, that avoid the need for an engineer to do this kind of feature generation? One thing I'm still trying to wrap my head around, and this may be more of a personal request than anything that needs to be especially novel, but anomaly detection seems to be one of the big things that people want when they actually want to deploy battery-powered devices in an environment. And they want to know, hey, I'm sitting on a machine that's vibrating, let me know when it's vibrating weird. And that's a super hard problem because each machine may be vibrating differently when you put the device on there. And you kind of want to know when there's a change, when there's an anomaly. But how do you do that without learning? Or do you need training as part of that anomaly detection? That feels like a wide open area that would be incredibly valuable to a lot of people if we could solve some problems there. I can never get enough data sets and benchmarks. I feel like a lot of our work as a community is really hamstrung by the fact that we don't have the kind of data sets and shared benchmarks that we would like. So I am always happy to try and support anybody who's coming out with a data set that is useful as an open source way of representing some really interesting problem. And there are loads of people out there in the medical and agricultural and ecological sort of wildlife tracking world who could do with our help. Let's see if we can actually do some cross-disciplinary papers and research to show what we're doing on device is actually important. And I want us to sort of leave really thinking about how we progress after this workshop. Hopefully you've made a bunch of personal contacts, but if we have 2 minutes, I would be really interested on people's thoughts on how we can actually carry this momentum forward that we've built up during today.
So Pete, I have one question for you. I think most of us probably curious. What's the plan? Do you and your team have plan to make effort to include more compression technique to Tensorflow Lite? For example, the supporting for arbitrary bit precision model?
That is a great question. We have been approached, especially around trying to actually add arbitrary compression into the file format so that you can actually do decompression on the fly, potentially, and there's increasing amounts of hardware that actually seem to support that. The tough part has actually been figuring out practical uses for less than 8 bits. Because it feels like there's this big gap between 8 bits is a really nice way of optimizing. You can do really fast software routines with 8 bits. If you go down to 6 bits, then kind of nothing fits with the hardware. And it's only until you get down to 1 bit that suddenly it's easy to write good software solutions that are optimal on existing hardware. So honestly, it's been this kind of chicken and egg situation that because we haven't had hardware that supports this well, we haven't had much of an effort to support it from software.
Okay, for that, let's send Peter for the great talk and closing remarks.
Okay, thank you, everyone.
Thank you.